Infinity feels like a single, endless thing. One giant, undifferentiated forever. Count forever and you will always find another number waiting. But here is a question that sounds almost silly until you sit with it. Are all infinities the same size? Could one infinity actually be bigger than another? It sounds like a contradiction in terms. Infinity is supposed to be the biggest thing there is, the thing beyond all measurement, beyond all comparison. How could there possibly be a bigger version of that? And yet, in 1891, a mathematician named Georg Cantor proved that infinity comes in different sizes, and he did it with an argument so simple, so visual, that you could sketch it on a napkin, and so devastating that it reshaped the foundations of mathematics. Some of Cantor's contemporaries found the result so unsettling that they rejected it outright. One prominent mathematician of the era called Cantor's work a disease that mathematics needed to be cured of. Others called it paradise. Both reactions were pointing at the same thing, that this small diagonal trick had touched something enormous. Let's start with the numbers you already trust. The natural numbers. 1, 2, 3, 4, and so on, marching upward forever. This is the most familiar kind of infinity. It's the infinity of counting. Whenever you can line things up against these counting numbers, one item per number, with nothing left over and nothing skipped, mathematicians say that the collection is countable. It doesn't matter if the process never finishes. What matters is that every single item eventually gets its own number. Now here's the real question Cantor was chasing. What about the real numbers? Not just the whole numbers, but every decimal in between, every point on the number line between 0 and 1. Numbers like 0.5, 0.333 repeating, 0.14159, and on forever without any pattern at all. There are infinitely many of these too, obviously. But is it the same infinity as the counting numbers? Could we, even in principle, pair up every single real number between 0 and 1 with a natural number, 1 to 1, leaving nothing out? Let's try. Suppose someone claims they've done it. They hand you a list. Row 1 is paired with some infinite decimal. Row 2 is paired with another. Row 3, another, and so on forever. They insist this list is complete. Every real number between 0 and 1, they say, appears somewhere on this list, matched to its own natural number. Picture this list as a table. Down the left side, the natural numbers 1, 2, 3, 4 climbing endlessly. Across from each one, its paired decimal, written out digit by digit, stretching infinitely to the right. Row 1 might read 0.14159 and keep going. Row 2 might read 0.50000 and keep going. Row 3, 0.33333, and so on. An infinite table, infinitely tall, and every row infinitely wide. Here is where Cantor does something beautiful. He doesn't try to search this infinite table for a missing number. Instead, he builds one, directly out of the table itself, using nothing but the table's own diagonal. Watch the diagonal. Take the first digit of row 1. Take the second digit of row 2. Take the third digit of row 3. The fourth digit of row 4. Keep going forever, one digit sliced out of each successive row, always moving one column further right as you move one row further down. This diagonal path touches every single row in the table exactly once, and it hands you a brand new, infinitely long string of digits. Now comes the trick that breaks everything open. Cantor doesn't just copy that diagonal string, he changes it. Every single digit he pulled out gets altered just a little. Add 1 to it, say, wrapping 9 back around to 0. It doesn't matter exactly how you change each digit, only that you change it to something different from what was there. Do this for every digit along the diagonal and you get a completely new number, built one digit at a time, straight out of the bones of the table. Let's make this concrete. Suppose the diagonal digits, pulled one from each row, happen to read 1, 5, 0, 3, 9, and so on forever. Add 1 to each of those, wrapping 9 into 0 as we go, and the new number begins 0.26140 and continues in exactly that fashion forever, one changed digit for every row of the table, no matter how far down that table extends. Now ask yourself a question. Can this new number already be somewhere on the list? Check row 1. The new number's first digit was deliberately changed from row 1's first digit, so the new number cannot be row 1, they disagree in at least that one place. Check row 2. The new number's second digit was changed from row 2's second digit, so it cannot be row 2 either. Check row 3. Same story, the third digit was altered specifically to disagree with row 3, and this pattern never stops. For any row you pick, no matter how far down the infinite list you go, the new number's digit at that exact position was built to be different from that row's digit at that exact position. That means the new number disagrees with every single row at some digit guaranteed. It cannot be row 1. It cannot be row 2. It cannot be row 1,000,000 or row 1,000,000,000 or any row with a natural number label at all. But it is still a perfectly valid real number between 0 and 1. It exists. You can write it down, digit by digit, as concretely as any other number on that list. So think about what just happened. We assumed the list was complete, that it captured every real number between 0 and 1, and yet we just constructed, using nothing but the list itself, a real number that the list does not contain. That's a contradiction. The list cannot have been complete after all. And this isn't a flaw in one particular attempt at a list. The same trick works no matter which list you hand Cantor. Any proposed pairing between natural numbers and real numbers, any attempt at all, produces its own missing diagonal number. There is no fixing it. There is no clever list that dodges the argument. The real numbers, provably, cannot be lined up one-to-one with the natural numbers. Which means something has to give. The counting numbers and the real numbers are both infinite, yes, but they are not the same infinity. The real numbers form a strictly larger infinity, an infinity so dense that no amount of counting, however endless, can ever catch up to it. Mathematicians call the infinity of the counting numbers Aleph-null, the smallest infinite size. The infinity of the real numbers is bigger, and it's called the continuum. And Cantor's argument shows, with total certainty, that the continuum is strictly larger than Aleph-null. This single idea cracked infinity wide open. It showed that infinite is not one size but a whole hierarchy of sizes, an endless tower of infinities, each one bigger than the last. Once you know how to build a diagonal number that escapes any list, you can apply the same trick again, one level up, and prove that even the continuum has an infinity bigger than it, and a bigger one after that. The tower never stops. There is no largest infinity, only an endless staircase of larger and larger ones, each too big to be counted by the one below it. And the proof of all this didn't require exotic machinery, no advanced equations, no specialized notation invented just for the occasion. It just required looking at a table, walking down its diagonal, and changing what you found there, one digit at a time. That is the strange elegance of the diagonal argument. It takes something as ordinary as a list of decimals and turns it into a mirror that reflects its own incompleteness back at itself. Sometimes the deepest cracks in our intuition open up with the simplest possible tool, a straight line drawn corner to corner through an infinite grid, quietly proving that some infinities will always be bigger than others.